Okay, we are trying to solve problem 3.14, and basically water is flowing around a bent curve, a circular curve at a constant velocity, and we are given that the outside radius of the tube is 6 meters and the inside is 4 meters. And basically we want to find the pressure at point 3 at the top and point 2 in the middle, given the pressure at the bottom. So they tell us that the velocity is 10 meters per second, and that's a constant velocity. And the pressure at the bottom is 40 kilopascals or 40,000 pascals. So, like I said, we want to find these two pressures. And to find those, we will use this equation. And we know that this equation applies because the 2 points we're trying to find are both perpendicular to the streamlines. So, in order to solve this equation, we need to know these constants. We need to know that the specific weight of water is 9,810 newtons per meter squared, and the density of water is 999 kilograms per meter cubed. So Matt will show you how to solve the rest of the equation.
Alright, first I guess we'll start with point 2. We can find the pressure at point 2. So we're using this equation. So we have P2 minus P1 is equal to negative gamma Z2 minus Z1 plus rho of water, the integral from R1 to R2, E squared over R dr. So now we'll go on. We know we're looking for P2. We know the pressure at 1, which is 40,000 pascals. That's equal to negative gamma, which is 9810 newtons per meter squared. And then we have Z2 minus Z1. Over here, we defined our datum at point 1. So Z at point 1 will be equal to 0, and Z at point 2 will be equal to 1 meter. So we have 1 meter minus 0 meters. And we have plus the density of water, which is 999 kilograms per meter cubed. And then we have that times the integral from R1, which is, and that's measured from the radius of curvature from the center. So R1 will be 6. And R2 will be 5. And inside we have 10 meters per second squared over R dr. So now we can go through and work through this, and we'll get, we go to P2 is equal to 40,000 pascals, and this will turn into 9,810 pascals, and then we have plus 18,213 pascals. We'll look at this integral right here. That's going to be, we can pull out the 100, so we can go 100, the integral from 5 to 6, 1 over R dr, and then 1 over the integral of 1 over R dr goes to the natural log of R from 6 to 5. And then we get a final answer of P2 equal to 12,000 pascals, which is equal to 12 kilopascals. Okay, so that's right there. We got P2 solved for. And P3 will basically be the same thing. So we'll look at that now. it will be the same thing, except we'll just solve between points 3 and 1 now. So we'll just change this to point 3. And then this will be Z3 now. And then we're solving between a radius of 3. So it's the exact same thing. We already know P3 minus 40,000 pascals is equal to negative gamma, which is 9810 again, newtons per meter squared, times Z3 minus Z1, and here we have, once again, our datum's down here, so Z1 is equal to 0, but now our Z3 is up here, and that's equal to 2 meters. So we have 2 meters minus 0 meters, plus the density of water, which is 999 kilograms per meter cubed, times the integral from R1, which is from the center of the radius of curvature, so that's going to be 6 meters. And then R3 is the distance from the center of the radius of curvature, which will be 4 meters. And then V is still uniform at 10 meters per second, and we square that over R dr. So it's basically the same thing, just plugging and chugging. Integral will be the same. 1 over R turns into the natural log of R, and we got a P3 equal to negative 20.1 kilopascals. And that's all. Thank you.